All right. It looks like our first speaker, Gustau, is having some connection issues, but maybe let's start with our second speaker. Mikey, are you ready maybe to give your talk first? And sorry to put you on the spot. And it's my pleasure to introduce our speaker today, Mikey Sonnenwald. She recently was a co-author of a famous Nature Machine Learning Intelligence paper, which outlined many challenges and opportunities of using physically informed machine learning for climate sciences. And we're very much looking forward to your talk. So please go ahead and share your screen. And apologies everyone for the connection issues.
Yeah, hopefully I'll manage. Let's see. I hope you can see this now.
Yes, that's perfect. Yeah.
Excellent. Right, yeah, so thank you very much for having me. I'm joining you from the land and waters of the Coast Salish people, and I'll be talking to you about how we can design a robust blueprint for trustworthy AI within climate science. And climate science is something that we often think about as happening mainly on land. We feel the temperature, of course, and other climate disasters, but actually a lot of the heat that's been put into our system is actually accumulating in the ocean, over 90%. So of course, understanding how the ocean is acting and understanding how the ocean might be changing is really important. And that's something we'll be focusing on in this talk on the North Atlantic specifically, where this is a figure showing lots of different studies that have come out demonstrating how the oceans are changing and what impact that has. And this is from the Intergovernmental Panel on Climate Change's 6th Assessment Report. Sorry, my system is being a little bit slow as well. There we go. All right, so when we think about the ocean a lot of the time, we can think of this as a set of emergent behaviors. And here you see just a figure showing that we have warm surface currents, and in the ocean, in the North Atlantic, they're brought up to the higher latitudes and made dense and then sink. So in this sense, we have several layers of currents going on. I'm not sure why my slides aren't advancing. Here we go. Maybe there's just a bit of a lag. But so when we think about the ocean, actually, of course, it's much more complicated than this very simplistic cartoon. And here's a figure from the ECHO model, high resolution model, just a snapshot from the surface. And we can see here as well that there are emergent behaviors here. The temperature is denoted with the colors, where within the equator, there's clearly some emergent patterns that change when you move to the higher latitudes. And seeing and figuring out where to draw the boundaries between these emergent patterns, between different drivers, say where the wind stress is very important for making the ocean move, is something that's very difficult to do with conventional classical methods. And similarly, what's really difficult is also then inferring what's happening in depth, which of course, both of these are very important for understanding changes in climate. And if we're looking at just the North Atlantic, here's another cartoon where you can see these currents being brought up along the east coast of the United States. Here, the breadth indicates the strength, and red is still warm currents. They're then brought up across the Atlantic basin to sink and cool in the higher latitudes. And this Atlantic meridional or north-south overturning circulation really has profound impact on the climate on Europe, also atmospheric patterns, droughts, sea level, and hurricanes. And it also exhibits what's called tipping point behavior, so it can change very rapidly. This is even featured in a Hollywood movie, The Day After Tomorrow. But when we're looking at these circulation patterns, a lot of the time within climate work, we have to simplify them quite a lot, to the extent that a lot of the time this very complex overturning pattern is is represented just with one very simplistic flow metric. And excellent. And within a climate context, this simplicity is out of necessity a lot of the time, because what we use is nominally often from the Coupled Climate Intercomparison Project, or CMIP for short. And CMIP is a wonderful tool. It's a set of climate simulations of models where you have a land and ocean component. They're very big efforts. And for CMIP, a lot of modeling centers across the world contribute their climate models, and it's a standardized experiment framework. So we can really compare what different models tell us might happen in the future. But for the Atlantic meridional overturning circulation, here representing this with just one number, out of necessity, is something that leads us to figures like down here, where all the colors are the different models. And we can see that there's clearly a change in the strength here on the bottom, the changes here on the y-axis. But this leaves us with a tremendous knowledge gap, because we don't really have access to, for example, as an oceanographer, all the fields that we would need to really understand the in-depth circulation. So sometimes we're even confined just to the surface. And this is where I believe machine learning can come in and really help for all of these fundamental questions. But I think for climate analysis, it's really important that we do this in a transparent way, or in a trustworthy way, which for me, I define as having an interpretable component and an explainable component. And together, these, I think, form what I refer to as transparency. An interpretable AI here is one where we can decompose it and really understand the different components, where explainability is more sort of a post hoc process where we can go and see what in the inputs led to our predictions. And of course, we know that within a more sort of black box approach, we can have a lot of bias throughout the process, where, for example, the data we choose can mean that if you were to try to do some facial recognition, having a white face makes the algorithm more able to assess nuances, rather than if you say were black. And within physical oceanography and the wider earth sciences, we can really pay for the free lunch of predictability that that machine learning gives us by having domain knowledge, by having access to the physics and the equations. And for this type of climate work, I would argue that this helps us increase our scientific confidence, and also the interest in the work. So in terms of this, just to highlight, we're trying to address some fundamental questions here and do this with machine learning as a tool. And these are whether or not there are fundamental regimes in the ocean, and whether or not we can infer subsurface circulation just using the depths. And the monsters here under the surface, of course, are the changes within the ocean for potential future climate change. And the algorithm here is called Tracking Global Heating with Ocean Regimes, or FLOR for short. And here you see an outline where step A is what I call interpretable, step B then is explainable, and step C is where we actually apply this to a climate model. So in terms of defining these ocean regimes in step A, what we start with is a full complexity climate model, ocean model, sorry, this is echo at 1 degree. And if you start naively with the full momentum equations, you have a very large amount of data, and also a very large amount of parameters. So your parameter space is somewhat intractable. But with my physical knowledge as a physical oceanographer, we can use theory to reduce this, performing an equation transform to both make things more interpretable, but also reduce the dimensions. And this is what you see here to the right. This is the equation we wound up with, describing the different drivers in the ocean. So we haven't left anything out, but we've arrived at these two-dimensional fields describing for each latitude and longitude what's making the ocean move. And to do this, then we can search within the space for those patterns of different areas where certain drivers are uniquely combined to make the ocean move. And we did this using k-means clustering, so mathematically tractable, and developing a specific geoscientific model selection criteria as well. And so here they are. There are 6 different dynamical regimes we arrived at in this model. And just looking specifically at the North Atlantic here, we can draw a cartoon of the circulation where then these dynamical regimes can tell us what's happening below the surface. And here, for example, this blue streak is telling us that we have this heat delivery across the basin, and the stacking of different regimes here along the coast of the United States tells us that this very intense current is moving along and moving upwards. So in this sense, we gain dynamic interpretability, which helps us move on to step B here, where we're going to be tracking these. And this tracking is effectively a mapping, of course, from input parameters that we can now choose, and we can choose them on the basis of knowing what these dynamical regimes are and what is important for them. And we can also choose them to be more appropriate for analyzing the climate models, where we know that the fields that are readily available are sometimes confined just to the surface. So in this sense, the input parameters or input fields that we decided to work with, because we know we can extract them from these very big, complicated climate models, was the wind stress curl, the depth, and the sea surface height. And having this now, we could design an ensemble of multi-layer perceptrons, or MLPs, where we wound up with 50 of them with the same architecture, but different initializations. These had 4 layers, and we used a Keras tuner for the hyperparameters. And for this class prediction, then we took the average softmax probabilities of them. There we go. Just to highlight the process here a little bit more, you can effectively bring your own climate model or idealized model or what have you, extract these surface fields, and then run it through this ensemble of multi-layer perceptrons. And this is what Thor is. And with this, then we can take the mean of these predictions to find the most probable class in this hitherto unseen model, and start to understand what's happening at depth. And having designed this as well gives us some unique capabilities in terms of explaining why the algorithm made the predictions that it did. And we did this using additive feature attribution method called layer-wise relevance propagation, or LRPs. And this is a post hoc method where initially, if you have trained a neural network here with different nodes, you can then propagate backwards and look at what these weights were to understand which part of the input actually gave rise to these predictions. So here, the example is predicting the cat, and we can see that we can sort of see the outline of the cat, which might give us a little bit more confidence that we can similarly recognize a cat in other situations. But of course, that's not what we're doing here within climate work. So here we're trying to ensure that we've actually learned something about the physics, because the basic physics are probably not going to change in a different climate. And here you see an example of what we found. So here are the input features. And on the top here, we have the different dynamical regimes, and just honing in on 2 of them. I put the equations that we started here on the bottom, where for this dynamical regime in the middle, we can effectively cross out 3 of them. So 3 of them aren't necessarily very important, but the wind stress curl here is very important. And we can see that this has very strong positive relevance, which is exactly what we expect. But on the other hand, if we look at this term that I crossed out, it has a grad H in it. So it really cares about whether or not there is a gradient variability within the depth here, the H field. And indeed, this is something that we can see here. Down here, there's what's called a ridge, a mid-Atlantic ridge, which is effectively a series of undersea mountains. So there's a lot of variability in the bathymetry here, and this is actively unhelpful for the network. While in these other areas within H, we know that it's more flat, and this is actively helpful. So in that sense, I can go back and unpick these dynamical regime predictions to say, yes, this makes sense. I trust this prediction. So in that sense, we can then move on and apply this to a climate change scenario. And here, the model that we're going to be using is a completely unseen model. It's part of this the CMIP ensemble, the geophysical fluid dynamics Earth system model. And here's a zonal image of the meridional overturning in the Atlantic, where in the historical sense, it's vigorous. The intensity of the red is what represents this. And we have this warm inflow at the top that then cools and is returned. And for a 1% CO2 scenario where CO2 is increased by 1% every year, and we look at this after 140 years, we can see that this is weakened. The color is less. And in a 4 times abrupt CO2 increase, so abruptly we quadruple the CO2 in the atmosphere, and again look at it after 140 years, this is weakened. And for this now, if we look at the different look at the different signatures that we expect from this circulation change, this includes having this current along the east coast of the United States shifting north, the heat delivery not making it as far up, and also the areas where these deep waters are formed, changing their location. So applying this to Thor now, we know that the EMF is going to be weakening, and extracting these surface fields from these different circulations. These are the patterns we find. So this is the Thor application, and just to guide our eyes a little bit, I've just drawn some of the lines on here where we can see that this current along the east coast of the United States is indeed shifting northwards, while this heat delivery north across the basin initially fans out quite a lot, but then increasingly becomes narrower. And this area of deep water formation also moves from being sort of confined to this area to winding up in this area, the Labrador Sea, where we know that the dense waters that are formed are probably lighter, so this downwelling is probably going to be less vigorous. And having this now, we can go and look at the different IPCC models, so the different climate models, and run Thor on these. And this is useful, for example, for comparing the different models again. And the IPSL model is a French model. And here we can see that there's a lot of variability in this pink area. It sort of grows quite a lot northward, which tells us something potentially about how it's interacting with the winds. While the CESM model, another American model, has a wide change in how this blue transport is happening across the North Atlantic. So in that sense, I can compare and infer what the different changes were that were together leading to this emergent feature of having the Atlantic meridional overturning decrease in strength, which of course allows me to unpick figures like this on the bottom right that we saw earlier in this talk, where we then know that there is weakening, but now we can actually tie it to specific mechanisms. And then, of course, also help improve the models because we know a little bit more about the actual processes that are underlying the changes. And with that, I'm going to start my summary here, hoping to have given Gustau a little bit more time, where Thor is really just designed for transparency. With this, I mean that we've taken care to have an interpretable AI core to this work, which gave us the ability to really engineer a data set to work with that can then be used to explain the skill of the predictions. And this is, I would argue, really central to climate applications of machine learning in general, because this transparency can boost our confidence in out-of-sample applications and really allow us to make what we're doing knowledge guided. And in terms of also having access to more dynamical knowledge within the CMIP applications, this could be a way of helping the dissemination hurdle and also allowing more analysis, or more in-depth analysis. And I hope this can serve as a blueprint for other applications also within wider earth sciences. But I also wanted to end with some open questions here, where I think having a platform like this with Climate Change AI is great, because we can actually start having conversations even across disciplines. And one thing that I want to highlight is that having reliable AI, especially in terms of explainable AI, is something that I think is really important. And I also wanted to highlight some of the other things we're doing with Thor. We're looking at different areas in the ocean, and also hoping to run it in terms with the model diagnostics task force package, to be able to actually do this model improvement. And there's also a Thor cloud application available that you can go and play with these things without having to download anything or have access to HPC, which is something that I also think is very important, because making climate science more equitable in the sense that we can all do it. We don't have to be at an institution with HPC is something that I think will really also help us make progress. And with that, I want to end also highlighting the review article that Cassia mentioned in the start. We also have one specifically for machine learning within oceanography. And I invite you to go check out the code for Thor. There's also a little how-to about how to access this cloud. You just need to get some cloud credits, and there's an avenue for doing that. And with that, I also want to thank my collaborators very much, and all of you for your time.
Thank you so much, Mikey. This was a very interesting talk, and there's several questions in the chat. So maybe I would suggest we go on with the next talk right now, and feel free to answer those questions in the chat, and then later we'll also maybe bring up some questions for general discussion between you and Gustau. But thanks so much. This was super interesting. And let's hope, Gustau, are you able to connect now? So maybe we'll be able to see your talk.
Yes, I'm here, but I'm connected through my mobile phone. So if you allow me, I won't share the video.
Yeah, that might be a good idea. Yeah.
Let me try to share screen. Yeah. You should
Perfect. Yeah, we can
something now.
Works well.
Okay, fantastic. Oh, well, first, sorry for the sudden interruption before. It never happened to me before, and I've been giving like online talks for 2 years, as most of you, right? Well, anyway, let me start. Well, hi everybody, and thanks for this kind invitation. It is always nice to talk, and it's even nicer to talk to such a diverse audience today. Also very close to my heart, because I'm a physicist by training, but also a machine learning by practice. These two fields, like machine learning and physics, they look like almost irreconcilable fields, right? Physics have been kind of traditionally relied on mechanistic models, let's say, to understand the system, while machine learning is typically on the other side of the pendulum, only relying on data most of the time, right? But after all, if you allow me this joke, both Kepler and LeCun, they both observe instantiations of a process, and they try to encapsulate those in a model that should be able to explain what is going on, and also a model that should predict well in almost all the cases that I've seen, and a model that can, at some extent, to extrapolate well to other similar circumstances. Well, in this talk, I will try to organize the field of physics-aware machine learning, which basically tries to combine or reconcile machine learning with physics. And I also want to convince you that machine learning or deep learning alone is not the solution to all our problems in geosciences. And essentially that we need to take like a little step back, think about the fundamental laws of physics governing the system, and exploit our domain knowledge together with observational data and simulations. Okay, so let's start. And let's start with this. This is our little nice object that we're concerned about, the Earth. What is the Earth's health status? What are the vital signs? What can we monitor it, predict its behavior and future state? Can we actually extrapolate its behavior into a kind of changing future? Can we do this in real time and ideally in an automatic manner? Well, in other words, what we want to do is inferences about the system. And for that, we use Earth observation data acquired by many platforms and sensor systems on the ground and many satellite sensors above our heads. And essentially, we use like a large computers, statistics, and machine learning models in order to estimate model essential climate variables, like the ones that you see in this video. Hopefully, you can see the video. We can now estimate properties of the land, ocean, and atmosphere with unprecedented accuracy. And we can run studies at either regional or global scales, right? And you can see it right. I mean, estimation, prediction, and characterization of these variables is perhaps the most important challenge that we are facing now. Because the system is changing, and we want to characterize a system that it is actually changing. So the rules and the observations probably they don't have much to say about the near future, but we have the physics to support these claims, right? So what we want to do here is to exploit all these kind of models that can predict, that can estimate, that can characterize these variables, and we want to do it efficiently. And we want also to incorporate some kind of domain knowledge to fulfill some reasonable, also physically meaningful predictions. And for that, probably you all know, it goes without saying that machine learning and deep learning in particular are advancing many fields of science, and earth science in particular. And these techniques allow us to solve very challenging problems like classification, regression, anomaly detection, parameter estimation with unprecedented accuracy, right? But now there are some challenges. Many, I would say, tons of machine learning models and applications are routinely applied in the earth sciences. But we are currently like witnessing a kind of collapse. Well, let me just briefly explain why. Well, the point is that the success of machine learning and deep learning methods is not incidental. So deep learning works very well in this kind of perfect storm where data exhibits some regularities. So spatial or temporal strong autocorrelations, like the same kind of in the video, image, or speech processing, for example. And that's why deep learning also works in earth sciences. Also, the success happens when big data is readily accessible, when one has a huge computational resources available and fast and scalable models. And thanks, I would say, thanks to these new infrastructures and the democratization of machine learning, code, and resources, this is actually possible now for a wider audience and wider practitioners. And last but not least, I would say that in 99% of the applications that you encounter in the literature of earth sciences, automatic machine learning is desired. So practitioners just want to reach high accuracy levels with a minimum effort, and if possible, automatically, without taking care of prior knowledge or trying to understand the system and just analyzing this problem via the prediction accuracy of whatever deep fat neural network. Well, I'm not really such a big fan of these 3 points, of the last 3 points. And a possible answer to resolve these big challenges is this field of physics-aware machine learning. You will find it in many different flavors, like guided machine learning, or informed physics-informed machine learning, or inspired machine learning, depending on the point of view that you adopt. Here we want basically to live in the machine learning physics interplay, and we want to exploit our domain knowledge and incorporate it in meaningful ways into the machine learning pipeline. The goal essentially is to attain consistency, efficiency, some sort of interpretability as well, and if you're lucky, some sort of extrapolation capabilities. And this is actually an old aspiration, as old as this old saying, right? Models without data, fantasy, data without models are chaos, or kind of. Well, in recent years, there's a high interest in combining purely data-driven machine learning with physics laws and constraints. And in this simple survey, we proposed like a very simple taxonomy. We summarized the different approaches where to live in the physics machine learning interplay for the Earth data analysis. We have basically algorithms that blend data and model simulations, methods that also try to approximate like costly models, physical models, like radiative transfer models with machine learning, methods that can learn the input state or parameter multidimensional distribution from observational data and prior knowledge, and methods that incorporate like differential equations, either ordinary or partial, into machine learning. Let me summarize what it's all about in this six simple examples where machine learning and physics meet for the earth sciences. And I should basically apologize for the shameless self-promotion because some of the methods are ours. And let me jump to the first one. Okay, so this is like the first approach. The idea here is to basically, okay, once that you're facing a classification or regression problem, like classifying or detecting changes in satellite images or estimating quantities or parameters in particular regions from images as well, then you want to assure that you want to ensure some kind of consistency. The idea here is to include an extra regularization term instead of only looking for fitting and enforcing the standard regularizers like enforcing sparsity or smoothness. We aim to minimize here the sum of all impossible solutions guided by a physical model that you have in hand. Well, in the toy example, in the figure, the authors wanted to estimate the temperature at different depth layers in lakes, and they managed to impose the known relationship between temperature and density as a constraint optimization problem, where one minimizes all the discrepancies or inconsistencies of these implicitly estimated densities across lake layers. Well, results were more consistent in general, and in some cases even more accurate. We recently generalized that work to work with multiple physical rules and models, not just one. The idea came from the field of algorithmic fairness. So our regularizer was no longer based on the L2 norm of the laws of physical discrepancy, but on a statistical independence. We used for that the Hilbert-Schmidt independence criterion, which is the cross-covariance norm, and accounts basically for all higher order relationships between random variables. This independence criterion, called HSIC, is very simple to compute in practice. And when you plug it into a standard kernel-rich regression model, the solution of this fair kernel learning comes in closed-form solution, which is very cool. Also, we found like a very nice probabilistic interpretation. So adding this HSIC regularizer corresponds to modifying the prior of the function evaluations. And then the posterior mode in a Bayesian model comes with a modified GP prior. So treating the learning problem in a GP framework actually allows us to derive uncertainty estimates and hyperparameter tuning. It comes more or less easy with marginal likelihood maximization. So let me show you this in action in a very simple toy example. Here, we wanted to predict like global temperature anomalies while trying to be independent to natural factors like volcanic eruptions or changes in solar irradiance, and also alternatively to anthropogenic factors like greenhouse gas emissions or land use change. On the left-hand side, you can see the family of the different prediction functions for different values of these fair or consistent regularizer, which clearly demonstrate that you cannot predict well temperature anomalies being independent to anthropogenic factors. So you have to be dependent too, but not the other way around. In the middle plot, we summarize the results in a Pareto front, where we run different models trying to be independent to many factors and measure the trade-off between accuracy and independence. And on the right-hand side, we simply derive a kind of feature ranking out of this trade-off between dependency and accuracy. And we clearly see that the dominant factors are aerosols and greenhouse gas emissions as expected. Well, another example of constraint optimization. This third example is trying to impose or incorporate exact constraints, because in most of the cases, you're interested in ensuring like mass or energy conservation. So one could do it as before, just adding a term in the laws to be minimized that sums all energy terms, for example, that are computed at the output of the neural network. Another way is with this method that basically they add, the authors added a constraint layer here in red in the figure at the output of the regular network. One has to define this C matrix that basically couples X with Y or different components of the outputs of Y, let's say, if you want to ensure that, for example, sum to one constraints. The method ensures those constraints to be met exactly. I would say that this is a very highly recommendable paper. Okay, let's jump to the second form of interaction between machine learning and physics. In here, we basically wanted to combine information from different sources, from models, simulations, and from data. In this case, we formulated a new Gaussian process model that combines two kernel functions, one dedicated to observations coming from satellites, and the other to radiative transfer model simulations. The model was able to learn the relative relevance of each term to try to compensate or to correct for the lack of in situ measurements and try to fill in this space with simulations. We applied this to parameter retrieval of a particular parameter of interest for us in vegetation monitoring, which is leaf array index, so the amount of leaves per square meter, using satellite, in this case, I think it was Landsat observational data, and a particular model of vegetation called Proseo for the simulation part. Over different regions. Well, we observed improved accuracy and consistency between model and data was achieved, and in some cases, some also we could actually derive some indicators of extrapolation regions. And of course, being a GP, you can derive confidence intervals for the estimates. A third approach of combination of machine learning and physics is that tries to include first principles in the form of our ordinary differential equation in machine learning models. This is the case of this particular model that is called process convolution model, and in particular, the latent forest model GP, where basically we form a hierarchical structure with common features, and then the kernels encode the governing ODE equations. So the model structure basically defines some latent forces that are parameterized, in this case with a zero mean GP, with a particular covariance. Then one defines a coupling mechanism between the latent forces and the observed output, which basically encodes the ODE. And this essentially translates into defining a linear convolution operator derived from the ODE. Finally, the output is a linear combination of such pseudo outputs plus some noise. The point here is that only linear operations and GPs are involved here. So the final solution is a GP2. Now, the downside is that you have to derive the kernel function from the ODE that you want to incorporate, and that takes some time to derive. Let me show this in action again. So we have used this model in many different problems. For example, to fuse different microwave sensors to estimate soil moisture, while respecting very simple, for example, a very simple first order ODE that relates soil moisture and precipitation. The method essentially can fill in the gaps of all the time series by importing information across time, across sensors, and across space as well. So the figure on the right shows you how this latent forest model fills in missing data and exploits information from some sensors to fill in the gaps in a period where the third sensor, the one at the bottom, was not even flying yet. Being a GP, in the end, the model also provides sensible confidence intervals for the predictions and extrapolation indicators as before. Okay, when you apply it to unseen data, the latent forest model can predict well for different sensors and can fill in the gaps very nicely, but there is more. Remember that we have encoded an ODE, and we can learn some parameters, and we can learn the latent forces. And the latent forces I mean, they are expressible. They can be plotted. Interestingly, the model learns some latent forces that basically we're driving soil moisture at the same time that they should respect the soil moisture precipitation relationship. But this was extracted without even seeing rainfall data. And we plotted here both the latent force and the precipitation, and they were highly correlated. So the model was actually discovering that the latent force was very, very related to rainfall, to precipitation. It was like trying to guess how much it rained by looking at how wet the soil is. And moreover, you learn the coefficients of this prescribed ODE that can be related to time decay, attenuation, damping, whatever. And then they have a physical meaning because they can be related also to the evaporation or runoff coefficients. Okay, this field of combining ODEs or PDEs and machine learning is becoming quite mature nowadays. And there are many, many different examples, especially in the literature of deep learning. And this philosophy is not new at all. Actually, look at this paper 15 years ago, where a hybrid model was already developed. Essentially, your neural network estimates enter an ODE along with some prior estimates, in this particular case of a particular chemical reaction, and the speed parameter is learned. The approach was, however, buried in the literature, essentially because one had to train at that time the modules separately. But now this has changed with the popularization of differential programming approaches, in particular in deep learning. We actually reviewed in a Nature Perspective paper the role and challenges in deep learning and proposed the integration of deep learning with process understanding as the way forward. On the left-hand side here, you have a general framework to physicize, let's say, deep learning models by including constraints in the network layers itself, not just as a constraint optimization problem, as we have seen before. While on the right-hand side, you see an example of a deep learning model that can learn motion fields that are accurate and physically consistent by including an extra layer that essentially works the motion field estimates with a physical model. The network weights are optimized end-to-end. Okay, this approach is able to effectively retrieve latent heat flux while constraining energy conservation in the surface energy budget. So you can see on the left, the standard non-energy conserving, let's say the pure machine learning model that tries to learn LE from some drivers. While on the right-hand side, the hybrid model decomposes the target LE in such a way that the energy conservation law is preserved. For that, of course, you have to define A, B, and C, or data. You can learn them from data. So this model basically showed better generalization, especially during extremes, showing like a very good potential for let's say global monitoring of droughts and heat waves. Okay, let's jump to the fifth way. No, as I said before, sometimes you know like different parts of the problem. You know, complete. Well, you don't know. You have like doubts about an uncertainty or high uncertainty or an unknown part, plus a more certain or accepted one, a mechanistic component, a model, let's say, that should be respected. So you can split the problem into different parts. Models typically come in the form of ODE or PDE, as we know. Another question is how to combine them. No? In this particular case, this is called the physics-informed neural networks. Essentially, here the authors were interested in predicting these variables as IR from time, but wanted to impose some restrictions on their time evolution. The idea here is to incorporate the known differential equations explicitly as an additional layer, parameterized with these alpha and beta that are present in the blue boxes equations. And then you can train everything end to end. So you can learn to predict, of course, your variables of interest, and you in turn also optimize the alpha and beta. So you learn something about the problem. Well, there's another way in which machine learning and physics interact. This is called, this is the problem where you want to replace a very costly physical model. And this is typically called emulation or surrogate modeling. So basically, through a fast machine learning model, you gain insight on the problem and allows you to run many more simulations of reality as you would do it with a standard physical model, because it is much faster, of course. Here, we typically use Gaussian processes and deep Gaussian processes because they excel also because of not only accuracy, but also because of the nice probabilistic treatment of the problem. You gain not only speed, once that the machine learning model is trained and you replace the physical model, you gain speed, of course, but also mathematical tractability in the case of GPs, because remember that they can provide you uncertainty propagation, uncertainty estimates, and also feature ranking for free. Look at the figures on the right, for example. You can hardly differentiate the rankings of the spectral channels obtained with the original data from the physical model and the different emulators with random forests, with Gaussian processes, with neural networks. Therefore, emulators actually encapsulated the physics pretty nicely and, of course, very efficiently. And finally, I would like to highlight that many problems in Earth observation and remote sensing, we are facing the problem of forward and inverse modeling. And in this case, essentially, you want to infer not only a particular emulator of the RTM, but also you want to learn this function F that translates observation into variable estimates. You may imagine that the RTMs are very costly, and you may want just a very simple retrieval algorithm, very simple in terms of efficiency and accuracy. Of course, you want as much as possible, but very often you are not only interested in recovering the variables or to estimate parameters as well, but you also want to learn about their distributions. No? And we are often facing this problem of learning these parametrizations and knowing what are the distributions of the parameters of the states given observations and simulations is very, very hard. In this work, we learn those parametrization densities in an RTM. Basically, the model gives like a Gaussian likelihood, and we assume a Gaussian prior. And then we want to fit to learn the prior parameters. The problem here is that integrating the RTM inside the Gaussian mean is really tough, though. But this can be solved by means of variational inference. We introduce the variational posterior into the log marginal likelihood. Then we choose the variational posterior to be Gaussian with a particular mean and covariance that are essentially learned with a neural network. And we take advantage of the well-known fact that the Kullbaum-Leibler divergence between two Gaussians is easy to compute and derive with respect to the parameters. So we can compute the expected value of the log likelihood. Well, the point is that unlike in the standard variational autoencoders literature, where the encoder is also a neural network, we have placed a deterministic forward model instead of a decoder network, and fixed the low. We basically fixed to a very low value of noise variance in the likelihood, in order basically to reflect that we trust the forward model. We don't think it is stochastic, but close to deterministic, right? The convergence time were basically orders of magnitude faster than more traditional or exact Monte Carlo or ABC approximations. And moreover, the variational inference scheme provides like a posterior approximation with a predictive mean and a covariance matrix. So you can not only predict, but also say something about the distribution of the parameters as well. In this case, in this example, we were able to learn the prior distributions of several lambda parameters like the canopy water content, chlorophyll, or dry matter. And all very popular and very free to use. So you have code for almost everything. So you have tons and tons of different packages that you can try it out and have fun with it, right? So I think for me this is really nice and very exciting because we are basically building the building, right? So we have now the theories, we have now the code, we have now the different applications, and this starts to be really promising and exciting. Let me just conclude with some final words. I would like just to remember 3 classical sayings in statistics and machine learning. Probably you know all of them. The first one, you can be right for the wrong reasons. The second one is something like, all models are wrong, some are useful. And the third one is an informal one in machine learning conferences that it says, AI is not deep learning, dude. And basically all 3 sayings emphasize better, more robust and consistent models as the only way forward to ensure a non-incremental advance, in particular for the earth sciences. Thank you very much.
Thank you very much, Gustau, for your very interesting talk. And likewise, Mikey, thanks so much for your earlier talk. We are slightly running out of time, but I think it will be very interesting to take up some of the audience questions and hear both of your answers, if you don't mind sparing a minute or two. So there are a few technical questions to Gustau, but I think maybe let's start with one question which is a little bit more open-ended, which I think it was an earlier question, and I think both of you would be great to answer. Machine learning generally performs weaker in extrapolation when new observations are out of the sample distribution, such as what climate change provides us. So to what extent can we argument that physics-learned algorithms are actually reliable for climate change projections, given that like our historical emissions will be different than our future emissions? And I'd love to hear both of your thoughts on that.
Should I start, Mikey?
Sure, I was just about to ask the same, but please feel free.
Okay. So just a random thought. I think this is a very interesting question. I always get the same one, and at least for me, the way it works is that, of course, you're having or you're intending to to do inferences about the system that is changing. And of course, you cannot trust you don't have enough observations of the system that it is changing, and you have like a very very solid background and knowledge about the system only through the physics that works, and they should be invariant to whatever situation the system is, right? With different parametrizations, of course, and changing all time. But the physics rules should actually be consistent and be preserved, right? So this is the very big challenge, right? How to fuse observational data with physics models, and learning that from the little observational data that we have, it makes me think that it is really hard to basically do extrapolation with only data. If you see this as an extrapolation problem, this is still an unresolved problem in statistics and machine learning. And the same thing happens when one wants to try to fit very accurately with physical models only. So I think that this is a very interesting and exciting way to combine both fields, trying to fit well in your observations and try to fit well in your unseen future, because you have like a background model that you can trust and you assume that it won't change much. But of course, this is like a bunch of theory that has to be tested, of course.
If I can jump in there as well. I think that is really one of the central issues, because climate change, of course, is per definition out of samples, so we don't have the data yet, and to some extent, this is at the core of what I'm also trying to address in my work, being grounded in theory. So being able to take this, take domain knowledge both within, for me, oceanography, and combine that with machine learning methods that really allow me to go back to verify that this prediction or the mapping that the neural network for me had uncovered was sort of at the core of the entire design of this blueprint. And I think that really considering this very carefully, and also considering what you would expect. So for me, I wasn't expecting the core dynamical regimes to change in the future, and there was a lot of thought that went into this, of course, where we were really analyzing also the dynamical balances that came out, and whether or not they conformed to what we thought they should look like. So in that sense, I think really combining both domain knowledge and machine learning is something that you can do very nicely. Also for really complicated sort of real problems, like analyzing the climate models that are actually actively used to do this work. But I think one thing I also want to highlight, somewhat in line with Gustau's words, is that we need improvements in some things like uncertainty quantification, especially for some of these explainable AI methods that have become increasingly popular, where really understanding the uncertainties involved, also because they help in the interpretation, is something that I think is very important. But yeah, that's a great question.
Yeah, thanks so much, both of you, for sharing. So maybe just a very quick follow-up question, like where do you think would be like the area of largest leverage? Is it in data, like for example, getting some more local data, like local knowledge from people, or is it exactly in like improving the models and like kind of still focusing more on the theory side? Where would you encourage the broader community of like people interested in machine learning and climate to focus? And I mean, there might not be correct answer, so it's more like an opinion question.
I mean, it's very hard to choose both. I think there's certainly a lot of scope for improving data collection, especially in areas where we know we're data poor. That in a climate context, of course, is under the ice, for example. We know this is changing, but I think there's also a lot of scope for improvement within techniques within climate modeling, for example. Parameterization was discussed in the two review papers that I mentioned on climate modeling, and also of course, focused on oceanography. Well, yeah, I find it very difficult to choose. Hopefully the community is big enough that we don't have to.
Thanks so much. Yeah, and Gustau, would you have any final thoughts on this question?
Yes, I think that in the future is really exciting, but we have to resolve both practical and theoretical questions before jumping into the real physics-aware machine learning. From the theoretical point of view, it is still clear when and how a hybrid model can work. So equifinality and identifiability issues, they are still unresolved. Of course, the extrapolation problem. And then when it comes to practice, we will have to face, data-hungry models and also data scarce problems. So we'll have to resolve all these issues concomitantly. So it's going to be like a tough pathway, I guess.
Yeah, thank you so much both for sharing and for your talks. They were very interesting. And to everyone involved here, feel free to join our community. We have a new community platform. It's called Circle or community.climatechange.ai. And we exactly, the idea is to kind of connect machine learning enthusiasts, climate researchers, and anyone else interested in tackling climate change. And hopefully we get to brainstorm more ideas and also find collaborators. So thanks everyone for coming, and thanks to our speakers. It seems like the audience very much enjoyed your talks. Thank you, everyone.
Thank you.
Thank you.
Thank you very much. Bye.
Bye.